So the so I think the next thing we'll look at here will be the um, tubing uh, the tubing rate equation. And this for dry gas is basically given by, again, this is our surface gas rate, by a very simple equation, which I'll write again C, but now I'll give it a subscript T for tubing. And what we're going to look at is a well configuration. It's a vertical well. This being the casing formation, and then we've got the tubing. And I'm going to just kind of mark where all the pressure. So down here we've got our flowing bottom hole pressure. And up here we've got what I'm going to refer to as the flowing tubing pressure, PT. And then I'm going to assume the well doesn't have a packer, even if it did. But basically just if it doesn't have a packer and you were to monitor the pressure in the annulus, at the top of the annulus, you'd get a pressure that I'm going to call PW. Okay. And then, of course, out here is the average reservoir pressure. You know, maybe no flow boundary out here. So the the first thing I want to talk about is for a static gas column, which this would be in the annulus, the way we're looking at this. So basically there's flow going through the tubing if there's no flow in the annulus, so we just have a static gas column. So if you just solve for a static gas column, and what you'll find is that the pressure at the bottom, well, let's say dP d depth is just the density of gas times the gravitational force. Okay, and if you put in the pressure dependence, pressure and temperature dependence, which varies with depth, this being molecular weight of the gas, or T, let's say we got the temperature in there. T, and then this is your Z. That. And you basically get a relationship for the difference between the pressure at the bottom is equal to the pressure at the top times a constant, approximately. That's assuming this is assuming that you can use some average Z factor in the gas column, some average temperature in the gas column, and this constant is usually referred to as, you integrate it out, you get a e to the s over 2. It's and sometimes you write in pressure squared. Like that. And S is a function of, the true vertical depth, the specific gravity of the gas, which comes into the molecular weight of the gas, basically. And it's got the average temperature and the average Z factor of gas. There's an equation for that. It's basically you get this constant. And what that then says is that if we look at if you look at the difference in pressure drop between, so the gravitational head of the gas is going to be essentially the same in both the annulus and the tubing. So what if you just look at the difference between these two pressures, like this is basically horizontal pipe flow type behavior, but it works for vertical flow because we've put these two pressures on the same depth reference, which is at the surface. Okay, so this so basically you've got a constant, and this constant is mainly a function of the pipe diameter because of the friction factor, because of the friction, the smaller the type, and it's a function of the inner diameter of the tubing to about the power of 2.7. It's also a function of the true vertical depth, or actually the actual length traveled if it's inclined, but I'll just put true vertical depth. And I believe also the S term may be in there, but mainly these are the two main factors of this constant. It's the length of flow through the tubing, so it's the tubing diameter, and the length of the tubing. So this is all for dry gas, and with basic approximations that you can relate so So again, for dry gas, the constant CT and the constant S, which is this gravitational term, remain unchanged through the entire life of the well. Just like the rate equation in the reservoir shouldn't change, the A and the B, or the C constant for the reservoir rate equation for Darcy. So okay, so these are basically the rate equation for dry gas, and then we'll come back and address how those may change, or whether the form of the equation can actually be used to match, for example, the multi-phase flow from the gray correlation for gas condensate or some other correlation. But the fundamental, most of the pressure drop is coming from the friction of the gas flowing through the tubing with some additional gravitational hydrostatic treatment that requires a change in the S and potentially the CT for the friction. So, but the same form of the equation is going to be very likely can be used for gas condensate wells also. It's just that you can't a priori calculate the CT and the S exactly for a gas condensate. Okay, so that's the rate equation for the tubing. Okay, and so for gas condensates, the changes are, we'll come back to that in the next session. Okay.